Period 1 of your exothermic and endothermic lesson. Is it on a book or piece of in your exercise books or a piece of paper? Just write the date, the title, keywords, the date, title, keywords, and then the starter. That should take you around 10 minutes. You'll want to work from hard, then harder, then hardest, in that order. Please do pause the video and then just restart after the 10 minutes or after you've completed it. Please use page 207 of your Pearson book if you need help, or BBC Bite Size. Okay, so these are the answers for the first question, hard. Exothermic is when heat energy is given out and it exits the reaction mixture and it goes into the surroundings. And the surroundings is actually the reaction mixture and everything around it that's holding the reaction mixture, like the container or the air around it. Endothermic is when heat energy is taken in and it enters the reaction mixture, and in here heat energy is actually converted into chemical energy in the bonds, stored within the bonds in the reaction mixture. And with exothermic you have chemical energy stored within the chemical bonds, like a fuel, let's say, and then the chemical energy, is transferred to heat energy. Then these, your combustion reaction, that's an exothermic because it releases heat. It feels hot. Hydrogen burning, again, that's a combustion reaction, so it's exothermic, releases lots of heat. Endothermic, that takes in energy from the surroundings. So photosynthesis takes in light energy. Your ice pack, that takes in heat energy from like the burn or whatever your ice pack is used to treat. And then thermal decomposition, that takes in heat energy from the Bunsen burner or the heat source. And in all of those cases, in your endothermic reactions, your heat energy is being taken in from the surroundings, then it's being converted into chemical energy that's still stored in the bonds. Then for hardest, we need to know how much energy a reaction emits or absorbs, as this can be useful in calculating how efficient a fuel is or how effective an ice pack is per se, but many other uses as well. So please take a screenshot of this sheet and then maybe you can copy and paste it into your OneNote and then just complete it. You can double click on these blanks and just complete the blanks here. That should take you around 10 minutes. You can use your Pearson book. Again, that's page 207 if you need, or BBC Bite Size. So with your exothermic reactions, your chemical energy, which is stored in your bonds, let's say fuel, for example, is converted to heat energy, and that's to the surroundings. And in your endothermic reaction, say heat energy from the surroundings, or let's say in photosynthesis, it's light energy instead. And your light energy from your surroundings is converted to chemical energy, and that's stored within the glucose molecule in photosynthesis. So your glucose molecule has lots of chemical energy. Now, if we look at the energy level diagrams, we can see here that the energy of the reactants in exothermic is higher than the chemical energy of the product. So this energy does actually refer to chemical energy of the reactants and the products. That's the same for this one as well, the same for endothermic as well. So just give an example, your fuel, which is your reactant, fuel and oxygen, your fuel has lots of chemical energy stored in the bonds. When you react it, it releases lots of energy, and the products therefore have lower chemical energy because all that chemical energy is being released to the surroundings. Now it's the opposite for endothermic. So if you have in photosynthesis, you have carbon dioxide and water as your reactants, and when they come together in light, they form glucose, which has a higher chemical energy, and we can use that. We can eat that as animals and use that chemical energy there for metabolism and many other things like Mrs. Nurg, all the things we need energy for. So we have a negative enthalpy change in exothermic reactions. So enthalpy change just means the heat change, which heat is measured in joules. So the heat change per mole, so this is kilojoules per mole, and it has a negative value in an exothermic reaction, and that's because you're minusing you're minusing chemical energy from the reactants to products, and it's the opposite for endothermic. You are adding your reactants and products are gaining chemical energy. Okay, so it's all about chemical energy from that point of view. So your exothermic feels hot to touch, and that's because your heat energy is coming from your chemical bonds in the reaction. And endothermic feels cold, and that's because heat is being drawn away from your hand into the chemical bonds in the reaction mixture. So you had to write down the type of reaction for the following reactions. So your magnesium, that is your magnesium and your sulfuric acid. This is a displacement reaction. That's because your magnesium is displacing the hydrogen. Because it's higher up in the reactivity series, it's displacing the hydrogen, and your hydrogen is now by itself. This is also a redox reaction because reduction and oxidation is happening at the same time. If you just Google what those are to remind yourself if you need. We can define redox reactions in terms of loss or gain of oxygen or loss of gain of electrons. So just be aware that there's two ways of defining redox reactions. Your sodium hydroxide and hydrochloric acid, this is a neutralization reaction, and that's because we're forming a salt plus water, and that's what neutralization reaction is. It's when an acid is neutralized to form salt and water. Your displacement reaction, this again is a displacement reaction because your aluminium is higher up in the reactivity series than iron, and it's therefore displacing your iron. It's also a redox reaction. And then our bottom two are combustion reactions. They're also oxidation reactions because they're reacting with oxygen, but they are also releasing lots of heat and light energy. So that they are specifically combustion, which is a type of oxidation reaction, which releases heat and light. So going over to our endothermic side now, your copper carbonate, when we add heat to our, it's bad handwriting, but when we add heat to copper carbonate, we break it down using heat. That's called thermal decomposition. So copper carbonate and zinc carbonate, and we can both break them down using heat. And then your enthalpy change, that is the amount of heat energy, and that's measured in joules. And we'll look in the next lesson, we'll look at how to calculate the heat energy in joules, taken in or given out in a reaction per mole. And your enthalpy change is measured in kilojoules per mole. So we'll look at how to work out joules, and then we'll look at how to work out moles, and then how to work out the enthalpy change from that. So it's kind of a three-step process in calculating the enthalpy change, which is up here. You need to first calculate the energy change, and then the number of moles that are involved in this reaction, and then you have to divide the heat energy by the moles to get your enthalpy change. Now, don't worry about that right yet. We'll look at that next lesson. So you have 3 videos here to watch, and you'll answer these 4 questions for each video. So it will take about 10 minutes. Watch video 1 and then answer the 4 questions, and then watch video 2. You can have video 2 as a subheading, and then answer the 4 questions, and then video 3, then answer the 4 questions. Your 4th question here, you'll be drawing 2 energy level either one of these energy level diagrams for the answer. And it's just a quick sketch. I'll suggest instead of writing energy, write chemical energy, because it does specify to that. That might help. There's also an optional real-life practical use of the thermite reaction video, and this just shows the thermite reaction in welding of railway tracks. You don't have to watch it, but it's pretty interesting, I thought. Now, this is an example of an endothermic reaction, as you've probably guessed, because the water froze. So your energy is coming from the surroundings and into the chemical bonds of the reaction of the reaction mixture. So it feels cold, and energy goes into the chemical bonds of the reaction mixture from the surroundings, i.e. the water, which then froze. And your hand, if you're touching it as well, you'll feel that it's cold. And this is the enthalpy level diagram. So your reactants of low energy, and then they gain energy from the surroundings, and they have a higher energy. Now, just to note that you can't just touch a chemical and tell if it's got a higher or lower energy. It's just like glucose. If you touch glucose versus water, they can both be the same temperature, but glucose has a higher chemical energy stored in it. You can eat glucose and release that chemical energy. Water, not the same. So just be careful here that this does not relate to temperature. It just relates to chemical energy, which you can't feel. The only way you can test for chemical energy is by burning it, and figuring out how much energy is released when you burn it. And so you can only really do it in combustion reactions, really. And there's other ways of doing it if not. Okay, so this reaction, chip pan fire, this is exothermic because the oil combusts, so that the oil already has to have already caught on fire first, and it's combusting slowly. If it's on fire, then you pour the water in. The water is denser than the oil. It sinks to the bottom, and the water actually vaporizes instantly. And when water turns to gas, it takes up around 1,000 times more space. So that water there that's now vaporized kind of just explodes out of the chip pan fire, and that causes all the oil to just shoot out, and the oil's already burning, and it just combusts and just kind of in a way explodes. So that's what happens there. It feels hot. You can see that. Energy goes into the surroundings from the chemical bonds and the oil is fuel. So this is the energy level diagram. That the reactants have a high chemical energy. So remember, this is chemical energy. You can write that there if it helps you. And the products have a lower chemical energy because all of that chemical energy is released as heat. And now the products have less chemical energy. But the temperature would be a lot higher of the products, okay? Because the products actually are part of the surroundings. Last one. This is exothermic. This is the thermite reaction. It feels very hot, and you know because the iron has melted. So it's so hot that it melts iron, and iron has a high melting point. So energy goes into the surroundings from the chemical bonds, and it goes into the iron and melts the iron, and into the ceramic pot here. You can see the ceramic pot's broken, and this is the reaction. This is iron oxide plus aluminium. Reacts to form aluminium oxide and iron. So you know this is a displacement reaction as well. Your aluminium displaces your iron because it's higher up in the reactivity series. Your energy level diagram, here it is. Your reactants are higher or have lots of chemical energy, and when they react, your products have low energy. So